Hi everyone, welcome back to another lecture for Design and Application of Lasers. That's Phys 4250 at the University of Windsor. I'm your instructor, Dr. TJ Hammond. This week we're going to be covering Chapter 6 from your textbook on pulsed lasers. So I've been marking your assignments over reading week, and I want to make a comment on the quality of work that I'm seeing. So this is a fourth year and graduate course. Solutions are meant to convey how much you understand the physics and the math and programming and all the tools that you need that are necessary to solve the problem. I'm getting a lot of like one-word answers for questions when I say, what is, the phase of this or something like that, and you guys just write pi by 2. I shouldn't need to say this for a fourth year class, but evidently I do. Show your work, okay? If you get some answer, you have to justify where that answer comes from. If you solved it analytically, if you have the analytic solution, show the steps that you took to solve it. That makes sense. What did you need to do to get to that answer? Same thing for if you solve something numerically, and this seems to be more so the problem, that if I give you code or if I get you to code something and you plot, and I say plot something, I'm seeing you guys plot an answer, and it's good that you guys are plotting something, but I really don't know what you're putting into it to get it to work. So just like you need to show your steps to solve for an analytic solution, I need to see your steps for when you are doing something numerically. Because if something's wrong, like if you've done something wrong with your differential equation or something like that, and you've put that into Python to solve, I don't know where you've gone wrong. Some of you are at least specifying what algorithm you're using to solve a differential equation, but most of you aren't. You're just giving the plot. So from now on, if I say plot something, I need you to justify where that plot comes from. I need to understand that you did your own work. Several of the plots from you guys looked very similar, which makes sense, but you have the same axes not labeled or mislabeled or something like that. And that starts to become quite suspicious. So I think I'm going to need to say show your work. If I say plot something, you need to show me the differential equation that you solved or whatever you're needing to plot, so that I can see how you solved it and how you attacked the problem. Okay. So yeah, math and coding are just the tools that we're using to model physics. They're there to back up your answer and justify it. So in particular for the differential equation that we had for the population, there was an analytic solution for that, and I'm sure you guys could see that on Wikipedia. But the differential equation for the intensity within a cavity, that one doesn't have an analytic solution. And so, you can solve it by Euler, you can solve it by midpoint, you can solve it by Runge-Kutta, you can solve it by the built-in ODE integrator. Any of those are fine, but I need to know how you solve that. So that's part of your answer. Okay. Plots also need labels. I saw a lot of people just giving a line. It looked like some kind of sigmoidal curve or something like that, but then didn't say what the axes were. What some of them said time, but it's like, what are the units? It doesn't mean anything if I just have some S-shaped curve. I need to know, in interesting timescales. Sometimes you can even have arbitrary units. So for example, for this problem with intensity, it was arbitrary units. It wasn't necessarily intensity in watts per meter squared. It was something that was proportional to the number of photons or proportional to the intensity, but the absolute value didn't matter. So you could say intensity, arbitrary units, and time, in microseconds or whatever it is. It doesn't really matter, but you need to know what you're plotting. It's nice to title them, at least if it's in like some part of a question. You should know. I should be able to know what you're referring to when you show me a plot. So I know, like, not necessarily all of you are going to be going into a career in physics, but you're trying to develop these skills for your career that you'll be using in a job after this. So of course, you'll be working in some group or something like that, and your boss will say to you, what is, some answer, and you'll need to produce this answer. And of course, your boss will want this right answer. They don't want you to give a wrong answer, just like I don't want to see a wrong answer on an assignment. Unfortunately, it does happen though. But you'll need to justify the answer. And so, if you have an accountant and you say, okay, how much money did we make last year? And you say $5, it's like, well, I hope that you actually have, the books to back up that answer, and you don't just believe them that they say you've made $5 this year. It'd be nice to know if that's what you think should be the answer, you can actually double check that that answer is correct. So the same thing is going to be with any job that you have. And so that's what we're kind of preparing you for by doing these assignments. So I want to see the right answer. That's, of course, ideal. But I definitely need to see your steps that you use to justify to get that answer. Okay, those are the skills that we're developing here. So I didn't think that I would need to discuss that at length for a fourth year course, but evidently I do. So here I am. Okay. We are now approaching, the halfway point of the course, and so I want to discuss the end of term projects. I discussed these at the beginning of the semester, but we've kind of let this slide. But I want to make sure that everybody knows that we should start to think about these end of term projects. So I still don't know what the final exam date is for this course, so I don't know when these are due. That date should be coming out soon though, and that will be the date that these things are due. And then that way, you'll have that time. There won't be a conflict during that time in order to hand in your assignment or your final project. I want all these projects to be unique. I want them to be done by you. I don't want them to be, something that you're working on with somebody else. I also want to make sure that the answers that you get are unique. As in, if some plot is already in your textbook or you found it in a paper or something like that, I don't want you to just copy it and paste it and say, this is what we would get if we put these numbers in. That doesn't, show that you've actually learned anything from this course. That means that you've learned, how to find the appropriate, like textbook chapter and then copy and paste something. That's not actually, physics. So what I want you to do is actually understand the physics that's either derived in your textbook or derived somewhere else, and you go through it, and then you end up with some answer, and then you end up plotting it or simulating it, and showing that you've done that yourself. So obviously I don't want to see code on a poster. That's not a good use of the poster space, but you'll have to submit your code for the simulations or your plots in a separate file. Okay, so we want to make sure that you learn physics with this. So for example, if you're writing about laser eye surgery or something like that, or laser surgery, there's really no physics. If you just say, like, we can cut skin with this, we can cut muscle with this, we can cut, what's the physics of that laser cutting into different things? Why would a certain laser work well for, say, cutting skin? Why would a different laser work well for cutting, something else? Why would a certain laser not work for cutting skin? That would be the thing that you'd have to understand and discuss. And of course, this is physics, so it would be good to have quantitative analysis. So if you want to say that you're, breaking some bond with this laser, well, I want to actually see how you're breaking that bond. Okay. So what could you do to optimize that bond breaking? How could you minimize the damage to surrounding tissue, all that kind of stuff. So that's the physics. So just kind of a summary, like, of the Wikipedia entry of something is not physics, and that won't be counted for very much. And yeah, so just to emphasize, the plots and simulations you have to do yourself. So if you take it from some reference and you just copy and paste it in, that's just going to be given a 0. I did projects for people last year, and I emphasized that, and I still saw people just copying and pasting something. That won't be counted. That will just be a 0. I'm giving you plenty of time in advance to know that that's the case. So if I see that, it won't count at all. If you have it included, it'll be like I'm just not, like I'm completely ignoring that. So yeah, as I said, posters to show your final results. Of course, it won't be able to show all the work that you did to get, to show that you put into the project. So submit code and any other like derivations that you might have needed to do that didn't make onto your poster, and I can count that as extra. So the goal of the topics for undergrads is topics that are covered in the textbook but not covered in class. And for grads, it's topics that aren't covered in the textbook. So you'll need to read some papers. Of course, I can point you in the direction of some of the papers. Okay. So some people email me at the beginning of term to discuss the project because you're working on something similar already. I discussed with your supervisor or supervisors of what you were working on, and we came to the conclusion that it's not exactly fair because you're already working on some project. So you're already, ahead of everybody else. And so I don't really want you to be able to submit that. It's also something that, we also want you to learn something, right? You're taking this course not just so you can reproduce something you're already working on. We want you to learn something in this course. So I want it can be tangentially related, but not directly related to what you're already, working on. So I've listed in this previous slide a bunch of ideas for undergrads that are in the textbook that we aren't going to be covering in class. And for grads, stuff that we're not going to be covering. There's some stuff that's not even in the textbook. But I've actually gone through a lot of those ideas and found, something that you might be interested in. So I have some suggestions, which will be on the next slide. If you don't like the suggestion that I've made, feel free to change with somebody else who agrees to obviously change their topic with you, or come to me and we can find maybe a different topic idea, or if you have an idea, come to me with a suggestion and we can see if it's appropriate for a fourth year, physics class or grad physics class. For undergrads, I expect you to put in about 20 to 30 hours of the work. For grads, about 30 to 40 hours of the work. Remember, for undergrads, it's a poster. And as I said, plus any coding derivations that you can't show in the poster. And for grads, it's a paper and a presentation. So it's another reason why I want this to be during the exam time, so that you guys can give a presentation of, some 20-minute presentation or so on what you've been researching, and everybody would be able to have time to be able to sit in on this and hear your presentation. Okay, so my suggestions. I put little notes next to it, like why it might be important. Not all of them have that. That doesn't mean it's not important. It probably means that it was simply predating when lasers were often awarded Nobel Prizes. So it turns out back in the 50s and 60s, in the 60s when the laser was invented, there weren't really any Nobel Prizes given out for this work, and that's because they basically said that this is just a new form of optics, just a new type of a light bulb. And initially people didn't really comprehend the quantum nature of a laser, even though they knew, from the beginning that it required, talking about photons and excited states and stuff like that. All that stuff is quantum. They didn't really realize that there was inherent quantum nature to the light emitted from a laser. So until really basically the 80s or so, there weren't really many Nobel Prizes awarded in optics. So things that were developed at the beginning, like density matrices, self-focusing, and optical parametric amplification, like second harmonic generation, things like that, even though those are quite important, they didn't lead to Nobel Prizes. But we'll discuss during lecture, these different projects, and you guys can comment on them. And as I say, if you don't like my suggestion, feel free to try and switch with someone, or we can find a section in the textbook that interests you, or if there's nothing, I have other optics textbooks that we can go through and maybe find something that's interesting to you. Okay, so I guess that will be it for that part, and then I'll create a new video that actually discusses the material that we'll be going through this week.